In this lecture, we will start with balls and bins, and then see an application of an application which is approximate median, where we actually use Chernoff bound, which you have seen in the last in the morning session. And then we will move on to if time permits, okay, geometric random variables and coupon collectors problem. So let's see how much we can go in 1 hour. Okay. So just a quick recap. So in the discrete probability space, we have like a pair omega and probability function. So omega is a countable set, and some of the elementary probabilities should be equal to 1. And the elements in omega are called elementary events, and a event is a subset of omega. And we know that the two events A and B, which are two subsets of omega, are independent if probability of A intersection B equal to probability of A times probability of B. Okay, what is probability of A intersection B? Sum of probabilities of elementary events in A intersection B. Okay, what is probability of A? Sum of elementary events in the probability of A. So if this holds, then this is those two events are independent. And then we also have seen something called the union bound. So today we will also see like application of union bound, which says that probability of A union B is at the most probability of A plus probability of B. Okay? And the other thing which we will see, to the last section of today, like last portion of today, is like using something called law of total probability. Law of total probability is very simple. Okay. So it says the following. Suppose you have like your omega, which is a set, and you have partitioned that into E1, E2, etc. up to ER. Partition means two of them intersect, and they cover entire thing. And suppose you pick an event A, then what is probability of A? Which will be summation of probability of A intersection EI, where summation is over I. Because you just need to sum it up this, sum it up this, sum it up this, sum it up this. Okay, so that's what called the law of total probability. Okay, so it's very simple. Okay, now the another notion we may use at the end of today's lecture is conditional probability. What is conditional probability? Conditioned on some event happen, what is the probability of some other event happen? What do I mean by conditioned on something happen? Okay, so suppose this is this is our omega, and A and B are two events. And when I say conditioned on B happened, I just need to restrict my sample space to B, which means that the sum of the weights of that probability weights within B should be equal to 1. How do you make it? You just multiply every element within B by a factor 1 by probability of B. Then, so if you multiply every element within B by 1 divided by probability of B, the summation of events within that way, because sum of the new weights within B will be equal to B. So you can think that B as a new a sample space where like, okay, B happened, now within that B what is going to happen. Okay, so that, okay, now if I want to say like, okay, what like probability of A, what is the probability of A happening given that B happened? Okay, so which means that when B happened, okay, this happened, so you are trying to do like everything, scale it up by 1 by probability of B, and then what is the probability of that within that A happened, which is this portion, which will be summation of this area total. So that, if you notice, that will be the old probability on the old probability terms. Suppose new PR prime of each of element here, say X here, you can think it as PR of X divided by PR of B. Okay, so then what is the probability of A given B will be equal to PR prime of A intersection B, which is actually equal to PR of A intersection B, probability of like that function PR of A intersection B divided by probability of B. That's all. Okay, so this is the definition. Okay. And then So I said, like, you are going to just restrict on B and then trying to calculate there. Okay? Or in other words, you just scale it up by a factor 1 by probability of B. That is the meaning that you are going to restrict on B. Okay? And you know that, okay, now I can write probably, law of total probability, where I can replace probability of A intersection EI with the probability of A given EI times probability of EI. Like, you just multiply, you just need to put this here, right? A intersection B or A intersection EI is equal to probability of A given EI times probability of EI. Okay, so this is another expression of law of total probability. Okay, this we will use at the last portion of the lecture. Yeah. Okay. So okay, that's just some basics of probability. Okay. Now again, we are going to do something called balls and beans. Like, let us. So this is a random experiment where we have some number of bins and some number of balls, and we are going to put each ball uniformly at random in one of the bins. Okay, and then we can talk about what is the maximum load a bin can have, and this you can think it as will have application when you do hashing and related stuff. Okay, so there are m balls and n bins, and each ball is thrown independently and uniformly in a bin, which means that each ball get into the first bin with probability 1 by n, and similarly for all other balls. And I want to understand properties of how much each bin, like the loads each bin will have, and this has many applications. Okay. Now, just define a random variable Zij. Is an indicator random variable for ball I falling into bin J, which means that Zij equal to 1. Zij equal to 1 if ball I fall into bin J, otherwise 0. Okay. Now, how many balls will be there in a bin J? So let's call it Xj. So Xj will be equal to summation over Zij. So J is fixed and I need to vary, like the number of balls, like which is like m balls are there. So you just vary like that index I. So which you are going to say like, okay, is the first ball land in J, the bin J, second ball land in J. Like if the first ball land in J, Z1J will be equal to 1. If the second ball land in J, then Z2J will be equal to 1. So how many balls will be there in a bin J? Xj will be equal to summation over I going from 1 to m Zij. Okay. And what about the other way around? Like, what is this is? The second line. Summation J going from 1 to n Zij, which is like, what will be that quantity? That quantity will always be 1, because, you just pick the ith ball and you are going to put it in one of them. So one of the Zij will be equal to 1 and rest of them will be 0. So this is like, this quantity is actually deterministically equal to 1. Okay. In case any doubt, please interrupt and ask. Now, okay, what is the probability, like what is the expected value of Zij? Okay, what is the probability that the ith ball land in jth bin? That will be 1 by n. The ith ball can land in one of the bins. There are n bins with uniform probability, like they are like independently and uniformly put into a bin. So the probability that Zij equal to 1 is actually equal to 1 by n, and 0 with 1 minus 1 by n, which means that the expected value of Zij equal to 1 by n. So what is a load in a bin J? That is Xj. what is the expected load in a bin J? The expected load in the bin J, xj will be equal to summation, like you just need to do this one. This is expectation of this one, set ij, where I going from 1 to m. And by linearity of expectation, what you will get is summation here, expectation of zij. And how many zij's you will be doing? M times. And for each of them, the expectation is 1 by n. And hence what you will get is m by n. So notice that if you are going to throw n balls into n bins, then in expectation each bin will have a load of 1. Like each bin will get 1. Okay. Suppose we want to ask the following question. Okay. We throw n balls in n bins. What is the expectation of the maximum load? What do I mean by maximum load? How is expected value of zij 1 by n for a particular bin? Okay. Okay. Now fix I, fix j. Okay. Fix I, fix j. Okay. Now I want to say, like, okay, when you are going to do this random process, the ith ball you are going to throw in one of the bins. And what is the probability that you will be ended up in J1? Yeah, that's the answer. The ball can fall in one of the n bins, and hence 1 by n. And that one bin is equal to J. That is what you are asking. That is 1 by n. Is that
sir?
Yes.
So that is clear with the respect of a particular ball, but for a particular bin, I'm asking. So we have m balls and n bins, right? Can you go back to the previous slide once?
Yep.
So m balls and n bins. So for a particular ball, it is equally likely that it will fall into one of the n bins. So we say 1 by n. That's okay. But from a particular bin's perspective, how is it n?
See, when I talk about when I talk about the Zij, what does it mean? What is the probability that ith ball fall in jth bin? Okay, and ith ball can fall in one of the n bins. It can fall in the first bin, or in the second bin, or in the third bin, or in the fourth bin, or in the jth bin, or in j+1 bin, like that in the nth bin. So ith ball can go into one of the n bins. Each of them will get probability 1 by n. And Zij equal to 1 when ith ball get into jth bin. So ith ball go into first bin with probability 1 by n, second bin with probability 1 by n, like that. And hence in the jth bin, it is going to with the probability 1 by n. And hence Zij equal to 1 with the probability 1 by n. Is that clear? Okay. So it's actually you fixed I and J, and you are talking about, okay, what happens when you do. Okay, good. Okay, now here is a question. Suppose we want to throw n balls into n bins. What is the expectation of a maximum load? What do I mean by maximum load? Look at the maximum of xj's. What is that? Okay. So notice that you cannot do like I cannot say like okay. What do you think? What is this?
So all the balls can fall in the same bin.
N.
That is of course an upper bound. What is the expectation of a maximum load? You got expectation of maximum load. This is the question.
1.
Is it 1?
Yeah.
See, the thing is like we're talking about expectation of maximum load. Okay. I cannot write this as a maximum of expected load. This I cannot write. I can have linearity of expectation, but this is not possible to write. Okay. So we'll see a proof. It is not one. It is like something called a log n divided by log n. Okay. So here, this is what we want to ask. Like, let y is equal to max over j going from 1 to n xj be the maximum load. We want to ask what is the expected value of y. Okay, what we will prove here is this is. Don't confuse, like you can have linearity of expectation. Like you cannot just simply out like f of x. This you cannot write. This is not possible. Okay.
So maximum load is maximum number of balls that can fall into any bin, right?
Yeah, like this is the expression. Look into each bin and which bin contain maximum balls.
Okay.
Like that. Not which, like that quantity.
Okay.
Not which one, like how many of them will be there. Okay.
Okay, got it.
So
okay.
Don't confuse, like you cannot simply apply like linearity. You just take it out and then summation you can do that, but not any other functions. Okay.
Okay.
So what we will see here is this we can prove. Like in expectation, the maximum load can be upper bounded by some constant times log n divided by log. Okay, natural logarithm. Okay. And how we prove that? We will use Chernoff bound to prove this first. So first we prove that, okay, the probability that y is, more than 12 log n divided by log n is bounded by 1 by n square. Once I prove that, you can apply expectation. How you apply expectation? Expected value of y is equal to, okay, probability that y less than 12 log n divided by log n times this quantity plus 1 minus this probability, whatever, times what is the maximum load within a bin? That upper bounded by n, right? That there are only n balls, n. And if I prove this to be at most 1 by n square, then this quantity will be at most 1 by n, which is very tiny, which is actually means that this probability is at most 1, right? 1 minus 1 by n square. So which means that in expectation, once I prove this one, in expectation, this will have, say, probably at most 13 log n divided by log n. Log n divided by. Is this clear? Sorry. Is this clear? See, assuming I proved this one, then the expectation of y is this quantity. Is that clear? If not, I will explain it again. Please let me know.
So how this 12?
Okay. Maybe. I would say like, so expected value of y is at most, what is the, okay, 12 log n divided by log n times probability that y is less than or equal to this quantity, 12 log n divided by log n plus n times probability that y greater than. Is this clear to you? Here I put at most. Is this part clear? This equation? See, what is the probability of y? See, y take value 1, 2, 3 up to n, right? Okay, 1 times what is the probability that y is equal to 1? 2 times what is the probability that this is equal to 2? 3 times what is the probability that this is equal to 3? Like that. So I can upper bound that to be, 12 log n divided by log n times probability that y is at most 12 times log n divided by log n. Clear? And for the remaining, what it is saying that, okay, okay, I'll call it delta. Okay, delta plus 1 times probability of, y is equal to delta plus 1 plus delta plus 2 times probability that y is equal to delta plus 2 plus etc. And at the end, n times probability that y is equal to n. That I can write at most n times delta value is at most n. Delta plus 1, delta plus 2, delta plus 3, all these values is at most n. So I can write that summation is at most n times the probability that y greater than 12 log n divided by log n. In case of any question, please ask. I will repeat it again. Like I will go one step below and then write it. Is it clear or not? Yes or no? It is okay if you didn't understood. Like then I will explain that. But then you need to tell you didn't understood. Then I will explain it again. So okay, good. So I see a couple of +1. So I assume it is +1 for all. Okay. So I just need to prove this, right? Probability that y greater than 12 log n divided by log n. Okay, so this I explained how to get it. Yeah, think about order only, not the lower bound. I just prove only upper bound here. Okay, now yeah. So what we do is, what we do is Chernoff bound. Okay, and what you have seen is union bound. So this is what I want to prove. Okay, probability that what we will do is using Chernoff bound and union bound, we will prove this. Okay, so how Chernoff not like sorry to say that what we have seen is union bound. What we have seen is not a union bound. It is just simply writing a term of expectation and then just upper bounding some of the terms. That's it. Okay, so to prove this one, we will use Chernoff bound and union bound. Okay, how we use Chernoff bound and union bound? Okay, we'll say that like how many bins are there? Like n bins are there. Okay, we'll say that okay, like I just fix one bin, and then I would say like okay, probability that the load within that bin is more than this quantity is bounded by 1 by n cube. Okay, that I prove using Chernoff bound, and then there are n bins. Now I would say like, okay, probability that in at least one of them, the load is more than this is bounded by summation of the probabilities of in each of them. It is like summation over j such that, in the jth bin, the load is more than 12 log n divided by log n. Okay, so there I use union bound. So Chernoff bound plus union bound. Okay, so that is a very well used combination. You use Chernoff bound and get probability so tiny. Like probability of failure is so tiny here, 1 by n square, right? So like in one bin, like how we do this one, in one bin, the probability that it contain more than this quantity, like what do I mean mentioned by here. So since I don't want to repeat this log n divided by log n, let me call this quantity to be delta. Okay. So see, the in any bin, something like the load is more than delta, that is a bad event. Okay. So how we do is, like, using Chernoff bound, we say like, okay, fix a bin. The probability that in that fixed bin, the load is more than delta is bounded by 1 by n cube. Okay. Notice that 1 by n cube is a tiny quantity. Suppose I have 1000 bins, then 1 by 1000 cube, it's like point, 0.00001. Okay, so very tiny quantity. Okay. Now then what we are going to say apply is union bound. Okay, what is the probability that xi greater than delta or x2 greater than delta, and like that will be like, there are n such terms. So by union bound we will have n times what is the probability that one of the xi greater than delta, that is n cube, and that we will get to be 1 by n square. So this is the template of like applying Chernoff bound and then union bound. Okay? So this is a very useful template. Okay? So as I mentioned, fix one bin and then talk about what is the probability that the load within this bin is more than delta. Okay, this is my quantity delta. Okay. And so it is like fixing one, like, yeah, fixing the first bin and talking about its load is also same as fixing the second bin and talking about its load, like, because they are all like equally likely. Like, so without loss of generality, fix the first bin and let x be this, x is the load within that. Okay, how does I can write x is the load within that summation of zi I going from 1 to n. What is zi? Sorry, zi equal to 1 when ith ball fall into first bin. Okay, so then I going from 1 to n, summation zi is equal to the load in the first bin. Okay, now what we want to upper bound is like this one. Okay, now we have already proved expected value of x, it's equal to how much, n by n, right? Expected value of zi is 1 by n, so there was zij. So we just thrown away that j, and then because like we just focused on first bin and then removed that one index, that's all. Okay, so expected value of zi, which is like probability that something getting into the first bin, like ith ball getting into the first bin, that is 1 by n. And so because of that, like there are n terms summing up here, so n times 1 by n, so we will get mu is equal to, or x mu, which is equal to expected value of x equal to 1. So in expectation, first ball contain, so first bin contain one bin. Okay. Now I just substitute 1 plus delta to be this quantity, this capital delta. Okay. And what we want to prove, like we want to upper bound this probability that x greater than 1 plus delta, and that is equal to capital delta, and mu equal to 1. So I can write the probability that x greater than 1 plus delta times mu. Okay, if you take out the notes of what you have seen in the morning section, so here small delta is greater than 1, and by Chernoff bound there is like one equation there which says that this quantity is upper bounded by e to the power minus 1 plus delta log 1 plus delta divided by 4 times mu. Okay, now mu equal to 1, so this will just 1, and then what is 1 plus delta? 1 plus delta is 12 log n divided by log n, and then there is a log of 1 plus delta. Log of 1 plus delta is log of, like, you will have log of log n divided by log of log n. That is a 12. And here you could cancel that. Like 1 plus delta, here I will have like, log n divided by log n. So this log n and this log n cancel. And you do simplification, what you will get eventually get is like e to the power, it is at most e to the power minus 3 times log n. And how much is this quantity? This quantity is n to the power minus 3. That is 1 by n cube. So the advantage of applying Chernow bound is like you have e to the power some quantity there. And if you can get that quantity to be some log n, like minus log n, then you will get 1 by n. That is a very tiny probability. That is what most of the application Chernow bound does. Like, so that's all. Like, so we proved that. Okay, so in the first bin, the probability that the load is more than capital delta is at most 1 by n cube. So now what you do? You do union bound. Let Aj be the event that in xj, in the jth bin, the load is more than capital delta. Okay. Now what is the probability that in one of the bin, like in one of the bins, the load is more than capital delta, which is upper bounded by, summation over the probability that in the load in the first bin is like, okay, like the load in the probability of load in first bin is more than delta plus the probability of load in second bin is more than delta plus etc. Okay? And that quantity is n times 1 by n cube, so 1 by n square. So this is what we proved. And if we have this one, then we know how to get that expectation bound we claimed that we have already proved. Any question? So is that fine? You understood it or not? Is the argument fine for this one? So did you understood this statement? Like, or like the proof of it? Yeah, okay, thank you. Okay, so this is, okay, this calculation we did, okay? So, okay, now we'll see a very simple algorithm to find an approximate median, okay? How many of you have seen an algorithm to find a median, like not an approximate median? Have you seen an algorithm to find median? Okay, what is median? Like given a sequence of numbers, okay, if you sort the numbers, which number will come in the middle? That is the median. Say for example, like if you have 2, 1, 3, 4, 8, 0, 1, 2, 3, 4, 5, 6, say 10. 1, 2, 3, 4, 5, 6, 7. Okay, now if I write 0, 1, 2, 3, 4, 8, 10, which comes in the middle? So here 3. 3 is the median. Okay, suppose you have like two numbers, like, okay, then here the median can be like one of those, like any of these is median. Okay. So have you seen an algorithm to compute median, like order an algorithm to compute median? Okay. Yes or no? BF Park algorithm. Yeah, some part. I don't know. It's called BF PRP algorithm. Like it's an algorithm by doing like it's a bit like slightly more involved algorithm. Okay? And so there is an algorithm like that, but so it's slightly bit more complicated. Okay, here we will see a very simple algorithm using partitioning. Yes, correct. Using partitioning strategy of quicksort. So here we will see like a very simple algorithm, but it will not give you, it will not give you a correct exact median. It will give you something in the sense that as follows. Okay, So here what I said, the rank is like, n by 2, or like seal n by 2 or floor n by 2. So what is the rank? Rank is like, if you sort it, like the ith element is called the rank I element, like which is the rank I element. When you sort it in the ith location, which element comes, that is called the rank I element. Okay. So essentially the median algorithm, median finding says that, okay, compute the element whose rank is n by 2. Or like n by 2 plus 1, okay, whatever that number is, like based on odd or even. Okay, so we have n distinct numbers, a1, a2, etc. up to n. Okay, and instead of like the rank n by 2 or n by 2 plus 1 element, I just allow like a little bit more space. Okay, so the rank should be between n by 4 or 3n by 4. Okay, how can you do it? Just very simple algorithm. Suppose I say like, okay, I want a number which is like whose rank is like, it's okay if it is not median, but it's close to median in the sense that its rank should be between n by 4 and 3n by 4. Any idea how to find such an element? Okay, rank. Okay, like what is a rank I element? Rank I element is like in the sorted list of this A1 to AN, which goes in the ith location. Like suppose like this is 4, 3, 2, 1. Then 1, like when I like this is like A1, A2, A3, A4. The rank 1 element is 1. Rank 2 element is 2. Or like if I put like a 0 here. Now then the rank 1 element is 0, rank 2 element is 1, rank 3 element is 2. So when you sort, which comes in the ith location? That is the rank I element. Yeah, that's with that you can actually find median itself, like do brute force, like sort and find it. But other algorithm, maybe like a constant time algorithm. So yeah, constant time algorithm in the RAM model. So the idea is very simple. Okay, uniformly at random pick one element from this A1 to A. What is the probability that its rank is between n by 4 and 3n by 4? Uniformly at random, 1 by 2. Yeah, that's it. It's a very simple algorithm, a probabilistic algorithm. Okay, just to sample with one number from this, like uniformly at random. Like any one of them will shows up with probability 1 by n. So how many of them are good? Like half of them are good. Like n by the elements whose ranks are like from n by 4 to 3n by 4, there are n by 2 such elements. They are all good elements. Okay, so any one of them is a good element. So that n by 2 divided by n, that is like 1 by 2. So with that probability, you're going to succeed. Now I ask you like, so now I make it slightly more complicated. Like instead of saying like, oh, okay, not I don't allow you to give like something which is like between n by 4 or 3n by 4. I want something which is very close to n by 2. In the sense, if you sort it, n by 2 is here, so you can go 1 minus epsilon times n by 2 here, and here also like 1 plus epsilon times n by 2. Like n by 2 is here. This is the rate. within this range. Okay, so if I choose epsilon to be very tiny, like 1 minus epsilon times, so yeah, epsilon to be very tiny, then it is very close, right? So the point is like you are allowed to go epsilon fraction to the left, epsilon times n by 2 to the left, and epsilon times n by 2 to the right. So if I choose epsilon to be 1 by 1000, then the n by 2 may be too far. Sorry, n by 4 may be too far. But this quantity will be like you can go only to only a length of n by 200, not n by 4 to the left. Okay? So if I want something within that tiny range, now how do I find it? We want an algorithm with success probability at least 1 by delta, where delta I will specify. Like I want, with probability 99%, like or like probability 0.99, I want to succeed. Okay? What do you think? Like how to go about such an algorithm? Randomly picking one, will it work? Randomly picking one will not work because its probability will depend on that tiny thing. Okay? So what do you think? If one of them doesn't give, then what is the natural strategy? See, we know that randomly picking one element is not good. So naturally, what is it? Okay, yeah, correct. Pick more numbers. Okay, pick more numbers, and then what you do? If you pick, like, say, 1000 numbers, now which one, like, how do you decide which one is your output median? Like close to that median, approximate median. Yes. Okay. Pick more, and then within that more numbers, pick the median of that numbers. Like so, sample a constant number of them, constant number of elements from the set A1 to An, and so but that constant is say 1000 or something. Okay, and then within that, like for that, like what you do is you pick the median of the sample, and that's like, and we will prove that for a carefully chosen constant which depends on delta and epsilon, the algorithm is correct. What do I mean by algorithm is correct? Algorithm will have this guarantee with probability this much. This guarantee with probability this much. Pick an extra epsilon n by 2 elements maybe. Okay, now the point is like if you if you are going to sample something which is order of n, and then you are going to find the median, then why don't you do it with that the input n numbers itself, because you are not going to save anything in terms of running time. Okay? So you don't want to pick order n elements in your random sample. Okay? So that actually kills the purpose. Okay, so what we do is k we will fix later. Okay, k is a constant that depends on epsilon and delta. Like, okay, so you can see epsilon and delta mentioned in this slide. Okay, with the replacement, what do I mean by with the replacement? Okay, so first you uniformly at random pick an element from 1, 2, 3 up to n. Okay, and then you are not going to delete that element from that 1, 2, 3 up to n. That still be there. And again, from that set itself, 1, 2, 3 up, like A1, A2, etc. up to An, are E and D related? You mean epsilon and delta? No, they are not related. Epsilon and delta are not related. So you can specify epsilon and delta. They are not related. So it's all like there is no relation. You can choose. You can choose epsilon to be 1 by 100, delta to be 1 by 1000. So it doesn't matter. Okay. So with the replacement, choose k elements. How do I mean? What do I mean by with the replacement? So pick one element uniformly at random from A1 to AN. Okay, that is the first. Again, pick one element uniformly at random from A1, A2, etc. up to AN. So it's you are not going to delete the element which you have already chosen. Like, or in other words, you may end up with the same element A1 k times. So that is possible. Like one of the outcome of the random experiment is like, you know, k number of A1. That is possible. That's what we mean by sample with replacement. So you just sample it and you have that, and still there is that element A1, A2, AN. You are going to again sample one element from it, like that. So there is a chance that, you know, one of the outcome is k number of AN. Okay, so that is possible. Okay. Okay. Now here is a theorem. Okay. So let k to be 1 by epsilon square log 1 by delta. Like, so that's like when epsilon and delta are constant, k is a constant. Suppose you sample k such elements with a replacement and say there is a condition epsilon less than half, and then the median of the median of the sample, median of this k elements, like the median of this k, the sample is actually an epsilon approximate median of the whole. What do I mean by epsilon approximate median? The median of the sample is actually an element which fits here in the input. Okay. And with a high probability, what do I mean by high probability? Probability at least 1 minus delta. Okay. Now, how do we prove it? Okay, so again, here we are going to use two things. One is Chernoff bound, and the second is union bound. Okay, S be the random sample chosen by the algorithm. So cardinality of S is equal to K. Like, okay. Imagine sorting these numbers, right? Imagine sorting not S like assume the sorted order of A1, A2, AN. Like A1, say, so like I want to say sorted order of A1, A2, AN, call it B1, B2, BN, B1, B2, etc. up to BN. This is the sorted order of A1, A2, AN. Okay, and now some like the middle portion is within this range, 1 minus epsilon n by 2 and 1 plus epsilon n by 2. So if your algorithm is going to output something from this middle range, your algorithm is correct. Okay, and so this portion is left and this portion is right. Okay, so this is left, this is right, and this is middle. Okay. In the left, how many elements are there? You know, 1 by, like the number of elements in the left, this side is 1 minus epsilon times n by 2. And in the right, how many elements are there? You do the calculation, you will get this also, 1 minus epsilon times n by 2. Okay. Now, suppose I have
Right
more
plus
than
epsilon, right?
What?
Right side has 1 plus n by 2, right?
No, right? Because what is it? Like how many elements are here? N minus 1 plus epsilon n by 2, which is actually n by 2 times 1 minus epsilon.
Can you please repeat? I didn't get. Can you please repeat once again?
Okay, so how many elements are here? Like what is the rank of this element? This element, the rank of this element is 1 plus epsilon n by 1 plus epsilon times n by 2. So the number of elements here is n minus 1 plus epsilon n by 2.
Okay.
And you get 1. So it's not the rank. It's like how many elements are there. Okay. Now here is the point. Okay. Suppose in my sample K, I have chosen at least k by 2 element from the middle, then the median of the sample will be within M. Also, or no, not that way. Okay, think a different way. Okay, sorry. Suppose you are not going to choose more than k by 2 from the left and more than k by 2 from the right, then the median of the sample will be here. Okay, so not the first statement. Okay, so here is the statement. Okay, listen carefully. Okay, suppose your sample does not contain more than k by 2 element from L and does not contain more than k by 2 element from the right R, then the median of your sample will be from M. Is the statement clear? Yes or no?
Yeah.
Okay. So which means that your algorithm make an error if either you choose more than k by 2 element from L or you choose more than k by 2 element from R. Okay. So it's a complement, right? Your algorithm will make an error if either your sample contain more than k by 2 element from L or your sample contain more than k by 2 element from R. Okay? Equivalent statement. Clear? Okay, good. Okay, so the algorithm make an error if this happens or this happens. Otherwise, we are good. Okay. Now, how do we do? Like again, we are going to apply Chernoff bound and union bound. Okay. Where do I apply Chernoff bound? To say that okay, this happens with a very small probability. This happens with probability at most delta by 2. Using Chernoff bound, we will prove. And again, like this, we will not prove. The argument is symmetric, so I will leave it. Again, by Chernoff bound, what we will prove is the probability of happening S intersection R is more than k by 2 is at most delta by 2. Okay. Then what do you apply? Like union bound. Probability of happening this or that is at most probability of happening S intersection L is greater than k by 2 plus probability of S intersection R is greater than k by 2, which is at most delta by 2 plus delta by 2, which is delta. Okay, that is the strategy. So once we prove this symmetric, so argument is symmetric, apply union bound. Okay, so we are going to prove this. Okay, and the other is symmetric, so I will leave it. Okay, so let y be the random variable which tells S intersection L. Okay, so y is a random variable which is cardinality of S intersection L. What is expected value of y? Okay, okay, what is y? I can write y to be summation I going from 1 to k xi, where xi is the indicator of the, okay, like the ith sample falling in L, like xi equal to 1 if ith sample, like ith element in the sample. Okay, ith element in the, what do I mean by, like you are going to do like sampling k elements, right? So the ith time when you sample like one element, that is going to sit in L, then I would say like xi equal to 1. Otherwise, it is 0. Okay. Now, what is y? Y is summation over xi. Okay. So xi is an indicator random variable, which says that the sample I is falling in L. Okay. Now, what is the probability that xi equal to 1? Probability that xi equal to 1. Notice that there are n elements. If you are going to choose n elements, what is the probability that it is going to sit in first 1, 2, 3 up to 1 minus epsilon divided by n by 2, which is 1 minus epsilon by 2. Is that clear? Probability that xi equal to 1 is equal to 1 minus epsilon divided by 2. There are n elements, and how many of them are there like in the L region? There are like 1 minus epsilon by 2, 1 minus epsilon whole divided by 2 times n. That many elements are there in L. So the probability that, xi equal to 1 is equal to this. Okay? Now, how many are there? How many samples are there? K samples are there. So summation y is equal to summation I going from 1 to k xi. So then what is expected value of xi? Expected value of xi is equal to probability of xi equal to 1 because it is an indicator random variable. Okay. Now what you get is like expected value of y is equal to k times this, and k times this is this. Okay, is this clear? Expected value of y is equal to k times 1 minus epsilon divided by 2. Is that clear? Okay. So apply Chernoff bound. What do I get? This quantity. Okay. So I will get, beta square will be epsilon square divided by 1 minus epsilon square. And for a mu, I have this term k times 1 minus epsilon divided by 2. When you do that simplification, I leave that. Okay. You will get this quantity. And suppose you substitute k to be, say maybe 12. Okay, 12 divided by epsilon square log 1 by delta, then that 6 will cancel, and then that will be there, and then you will get e to the power minus 2 log 1 by delta, or like, so here 2 by delta, and then you just do simplification. So essentially what I want to say is e to the power minus log 1 by delta is equal to delta. Okay. Now, if you have a constant here 2, then you will get it 2. So you choose here constant in such a way that you get a delta by 2. That's all. Like whether it is 10 or 12 or 20, it is just what constant you want here. Okay. But there should be a log 1 by delta, because e to the power log 1 by delta will be equal to delta. And what constant you want, accordingly, you put that number here, you will get delta divided by 2. Okay. So you do that simplification, what you will get is this quantity will be upper bounded by delta by 2. That's it. Probability that y greater than k by 2 is upper bounded by delta by 2. Okay. Now, similarly, what you can prove is you can say like, hey, let us take another random variable y prime, which is s intersection r, and I want to show that, okay, what is the probability that y prime greater than k by 2? Again, do the same procedure. What you will get is like it is at most delta by 2. Okay. And then do union bound, and probability at most delta, your algorithm makes a mistake. Okay. And with that, I will stop here. And any question? So what is the trick we have learned? Like how to apply Chernoff bound and union bound. It's a very nice template for randomized algorithm. How to apply Chernoff bound along with union bound to have like a to do like analysis of randomized algorithm. For example, here we did approximate median. How to find approximate median, like with very good probability, with very close to n by 2. And in the morning section, you have seen you have seen quicksort analysis again, right? With a good, like how can you say with good probability your learning time is small, like order and log n. And any question? Okay then, bye.